Hello, guys. So in this section, we're gonna talk about Unit 7, which talks about continuous random variables and also normal distributions. So let's begin. We're gonna review discrete random variables and continuous random variables. Says every discrete random variable X has a probability distribution table or probability histogram. Number two, we're able to find the probabilities of events in the form of an inequality that involves X using the probability distribution table or the histogram. Number three, we are also capable of finding and interpreting the mean and standard deviation of discrete random variable. So now the question that we want to ask, can we do the same for the continuous random variable? Well, let's take a look at continuous random variables. The definition, a continuous random variable is a random variable whose all possible values form a continuous interval. Some examples include the income of a randomly selected household. We are going to treat it as a continuous variable, even though if you round, income is usually reported rounded to a nearest cent, which is hundreds of dollars. So one can argue that it's not continuous random variable, and from that standpoint, I will agree with them. However, remember we mentioned earlier that when we have large values, large continuous values, large discrete values, we are gonna treat them as continuous random variable. It's just easier, even though technically it is a discrete random variable. Okay, so the next one, the exact lifetime of a randomly selected machinery, or the wait time and drive-through of a randomly selected customer. Again, the exact wait time, not rounded. And the last example is the incubation period of a virus for a randomly selected patient. All right, so I want to remind you about the discrete random variable histograms that we discussed. This is what they look like, right? So in these three histograms, we have the same data representation of the same data sample. So it's heights of males, let's say in a group, like in a class, for example. And we see the first one, we have a grouped data where the data is grouped in with the 4. The second is same data, but the group width is 2. And the last one is bin width is 1, so that means that it's not grouped at all. Those are all individual values with their relative frequencies. And what I want you to notice is how the width of the bar is changing. It's getting smaller and smaller, and the shape is slightly changing as well. Okay, so what happens with continuous random variables, that your width of the bar is becoming infinitely thin. So it becomes this it's so thin that each bar will be just this thin line. Okay, it doesn't have, so each bar doesn't have thickness anymore. So the area of each bar will equal to 0. So remember how we in a previous unit, we were talking about how the area of the bar represents its probability. The same concept is going to apply here to the continuous random variables, except let's discuss this. The probability of x equals 2 here using this histogram would equal to the area of the bar above 2, right? On the right side, the width of the bar above 2 is infinitely thin. So basically the area of that bar is 0. So when we're talking about continuous random variable, the probability that x equals exactly 2 is gonna equal to 0. So this question will not make sense. So instead of asking what's the probability that x equals exactly 2, for example, or exactly 2 or 3, which in the histogram on the left will be represented by 2 bars. Instead of that, we're going to ask the question, what's the probability that x is between 2 and 4, for example? Or another example. So here, this shaded region represents the probability that x is equals 7 or 8 or 9. So in the case with continuous random variables, we are going to ask what's the probability that x is between 7 and 9, including the endpoints. Let's talk about the graphs. So as we mentioned before, as we saw in the previous video, the width of the bars becomes smaller and smaller when we stop grouping, right? So, but with continuous random variables, we're gonna go even further. So it's not gonna, the width of the bar is not gonna stop at 1, but it's gonna become even thinner and thinner, infinitely thin, until each bar, as I mentioned before, doesn't have any area anymore. Now, what happens then? Well, let's take a look at this again, at this histogram. When we make a polygon by connecting the midpoints of each class, this is what we get approximately, right? This is the picture that we get. It's kind of normal. We see that similar shape, but it kind of not very smooth. I mean, smooth enough, but not perfectly smooth, right? And also we have some areas that are like sticking out from under the curve, and then there are some areas where it's empty under the curve. But in case of continuous variables, this line becomes very, very smooth and very, very on top of each bar that has a width of 0. So we don't have any gaps, right? We don't have anything that sticks out, and we don't have anything that's hollow under the curve. So this curve is smooth, and basically the area right under it represents our probabilities really, really well. Where right here, that would be approximate. If we used just this curve to calculate our probabilities, it would be approximate, just for that reason that we just mentioned. All right, so we are gonna have this curve for the probability, for the continuous random variable, which is called a probability density curve. We're going to call it a probability density curve. So let's take a look at the properties of the probability density curves. Property number one, it is always above or on the horizontal axis. So it's never going to go into negative values because remember, this curve, it represents probabilities, and probabilities are always values between 0 and 1. So they're never negative values. Another property, and that property stems from the fact that the total probabilities have to add up to 1. Remember, we mentioned that before. So the area under this density curve should add up to 1. So the total area under the curve is equal to 1. So these are the two properties of probability density curves. Now, let's take a look at some examples and see if they are or probability density curves or not. So here we have a couple of curves. Let's take a look. So here's some examples of some curves. So the first curve that we see is the graph of this equation, y equals 2 minus x squared. And we can see that this is not a probability density curve because it violates the item number 1, that it is always above or on the horizontal axis. So this one goes below, so it's not a probability density curve. Now, what about this one? It's the curve that described by the equation y equals 1/3, where x is between -1 and 2. Well, the first point is satisfied. It's above the x-axis. What about the total area under the curve equals to 1? Well, let's take a look. So this is our total area. So let's see. This is a rectangle, and the rectangle whose height is 1/3, right? So the area is height times width, and so the height is 1/3, and the width is from -1 to 2. So again, we have 3 units. So that's a 1. So it satisfies the second requirement. So therefore, yes, it is a density curve. All right, what about this one? Is this a density curve? Now, the equation here is y equals 1/8x, and the x is from 0 to 4. All right, so it satisfies the first requirement. The curve is above the x-axis. So that's, we have a check mark by that. What about the area? So remember, the formula for the area of the triangle is 1/2 base times height. Well, what is the base of this triangle right here? So the base is from 0 to 4. So the base is 4. Now, the question is, what's the height there? Well, the height is the y value when x equals 4. So what is that y value? It's 1/8 times 4, and that will be equal to 4/8. So that's going to be 1/2 when simplified. So basically, height of this triangle is 1/2. So let's put this information into our formula. I'm gonna write below here. So the area of this triangle is going to be 1/2 times the base, which is 4, times the height, which is 1/2. So what do we have? When we multiply, we have 4 divided by 4, which is 1. So the answer is yes, this is a probability density curve. In the next video, we're gonna review our probability rules and see how they will apply to our probability density curves and continuous variables.